Hello again. This is part 2 of chapter 1. We're going to start at section 1.4. First off, just a small review from last class. We talked about chemical and physical changes. We talked about if it's a chemical change, you cannot get back its original state, for instance, or original formula. For instance, if you take a match, you burn it, you can't get back its original chemical composition. However, if you had something like water, you froze it to ice, you could melt the ice and get back the original state of water. And that would be a physical change. The chemical change would be the burning of the match. We talked about intensive, extensive properties as well. We talked about pure substances. We talked about homogeneous mixtures versus heterogeneous mixtures. Homogeneous mixture is you see one thing, even though it's made up of several components. Heterogeneous mixture is you can separate it by physical means, whether it be distillation, whether you just use your hands and separate the pieces, whether you use filtration. And we also have a compound and element, which are pure substances. And then we touch base on things like everything should have a number and a unit when you report your answers, whether it be on an exam, whether it be in the laboratory. So we'll continue with section 1.4, scientific notation. On your exams, you should have a calculator, a non-graphics calculator, not your cell phone. You should really be one with your calculator because on exams, the last thing you want is to run out of time because you don't know how to do scientific notation, because you don't know how to use your log button if you need to use the log button. You need to be familiar, or the square root button, or the square button. You need to be familiar where these things are on your calculator so you don't lose time. So section 1.4, units of measurement, will continue. Again, Professor Kevin Mark, this is another resource for your regular lecture with your regular professor. Scientific notation. It's a way to write very large or small numbers in a compact form. For instance, if you have a cup of water and I were to ask you how many molecules of water were in that cup, you wouldn't write down, the 24, 25 zeros on your calculator. Your calculator wouldn't allow you to do that. Instead, if the question was how many molecules are in your cup, you write something like 1 times 10 to the 24. You couldn't do 1, 0, 0, 0, 0, 0, 0, 24 times. So we use scientific notation to express larger numbers or very tiny numbers. In this case, we have here 2.468 times 10 to the 8 meters. The number in the front should always be, the coefficient should always be between 1 and 10. That's just it's a standard way of writing scientific notation as its base. And the 8 here refers to the exponential. So let's just look straight to the example here. If I wanted to write 0.000423 in scientific notation, we would write 4.23 as our coefficient because, as I said, it has to be between 1 and 10. And we would move the decimal places here 4 times. Let's see if I can use the pen. We would move the decimal places 1, 2, 3, 4 times over to get 4.23 times 10 to the minus 4. On the next slide, this is an example type of calculator. You should be able to use or write these numbers on your calculator. 3 times 10 to the 4. In this case, looking at the calculator, we would write 3, followed by exponent, and then you would write 4. 3 to the exponent 4. And conversely, for a negative number, you'd have to write the negative number first. Write the negative number on this particular calculator, followed by 5.1, and then exponent again to the negative 12. Here again, 12. Okay? So practice this with your calculator. Okay, try to write these numbers on your calculator. It'll take you a while, a couple minutes to get used to it, but be familiar with this. So usually I ask class, write these in scientific notation. As I said in my first part of the lecture, in the previous slides, I'm going to put these answers on the Common Blackboard as well. So I want you guys to try on your own, and you can refer to the Common Blackboard slides, or sorry, answer key that I'll put later to check your answers. Or you can just check on the bottom here. Units, a metric system. We also mentioned last class about SI units. So the SI unit for length is meters. The SI unit for mass is kilogram. For time is second. For amount of substance is mole. So we're going to use this kilogram. We're going to use conversions, going from one to the other. So we have here some prefixes. Centi means 100. One way to remember this is how many years in a century. It's 100. Century, centi. We have millimeters, 1,000 millimeters in 1 meter. 1,000 milliliters in 1 liter. And we also have micro, 1 million microliters in 1 liter as well. And we'll do plenty of examples to get familiar with. I don't want to say you have to memorize this, but you will become familiar with this by doing many, many examples. Okay, the ones we should focus on: kilo, mega, centi, deci, milli, micro, nano, and pico as well. So there are two ways to write this. For instance, you could write 1 meter equals 100 centimeters. Centimeters. Or you can also write 1 centimeter equals to 0.01 meter. Both of these are equal comparisons. So again, here's an example. Let's use our knowledge. As I talked about at the beginning, we have our definitions or we have our notes. We need to apply these notes. So in this case, we have, the question is how many meters in 5 kilometers? So we write 5 kilometers. This is called a unit conversion. So just use the yellow. This is called a unit conversion, where we have 1,000 meters is equal to 1 kilometer. So if we write it out, if the question is how many meters are in 5 kilometers, we write out 5 kilometers. The answer we desire is in meters, so we write here our meters. And then we write our unit conversion, 1,000 meters over 1 kilometer. If you were to write 5K, 5 kilometers is 1 kilometer over 1,000 meters, the units would not cancel out. Notice in this example with the 5 kilometers, that will cancel out with the 1 kilometer on the bottom. Therefore, all you're left with is, as I circled in red, with meters to give you 5,000 meters. In the next example, we have how many grams in 1,000 micrograms. So we write out the question, 1,000 micrograms. The answer that we want is grams. Good. So we have grams here is what we desire for our answer. And we write our unit conversion, 1 microgram is 1 times 10 to the minus 6 grams. I don't expect you to know this offhand, but you will definitely have to be familiar with this as we keep going through the class. The micrograms will cancel, and all you're left with is grams in the final answer. This is a formula used to find Celsius. Again, our SI unit in general for temperature is Kelvin, but there are times in your exam you'll be asked to convert from one to the other, from Celsius to Fahrenheit, and if you're given Celsius and you want to convert to Kelvin, you have to add 273. So 0 degrees Celsius is 273 Kelvin. But again, this is the formula. Celsius is equal to 5 over 9 times Fahrenheit minus 32. And as I just said, if you want to find Kelvin, you have to add 273 to Celsius. Again, continuing with section 1.5, uncertainty in measurement, we will be dealing with exact and inexact values. We'll focus on the exact values. Those are things that are 100% for sure. We know there is 100 cents in a dollar. We know there are a dozen donuts has 144 donuts. 12 eggs is exactly 1 dozen donuts. So these are things that are called exact numbers, exact conversions. 1 meter is always 100 centimeters. 1 kilometer is always 1,000 meters. 1 meter is always 1 million micrometers. Okay, those are exact. The opposite is inexact. We can say inexact values. These are things that you measure, for instance, and these are usually depending on humans, depending on the instrument. If I were to ask each one of you to measure the weight of your cell phone, so or let's say my cell phone, if I gave you my cell phone to each one of you, each one of you go home and tell me a different mass. That's because maybe some of you would use your scale at home, some of you might take it to the market to use the scale, the fruit scale. You'd all give me different values, and that's because of the machine, the instrumentation that you use, and also that the human error, how you read the particular numbers, how do you define the mass of the cell phone. And you'll be doing this in the lab. Every time you make a measurement in the lab, there's going to be an associated error with it. If I ask what's the temperature outside, some of you might go to the thermometer, some of you might even look at your cell phones and find online. So you can have 75, you could tell me 75 degrees Fahrenheit, you could tell me 75.43, you could be even more exact or more precise. This would be an inexact. So as I just said, you would give me different values, 75, 75.4, 75.43. This is defined by usually the instrument. So here we would have 2 digits, 2 significant digits. I want this out in green. 2 significant digits for the first reading, 3 significant digits for the second reading, 75.4, and 4 significant figures, or 4 digits for the 75.43 reading. So the last digit, we would call that the uncertain value. As I just said, 2 significant digits for the first one, 3 significant digits for the second one, and 4 significant digits for the last one. The significant zeros, here we have 2, we have 3 digits, and 4 digits respectively. There's a set of rules that we need to follow for the rest of the class and the rest of your chemistry careers. There are significant figures. Here, in this case, there's about 5 or 6 rules that we need to follow. And again, you'll be familiar with these rules once through practice. Okay, so the first one is rule 0. I say all non-zero digits are significant. So in this case, 3, 4, 1, and 2. 3, 4, 1, and 2. 4 significant digits here. The second one, zeros between non-digits are significant. So if the number here is 808.3, the 0 here in the 10 column is considered significant. But again, if the question to the class, how many significant figures in this number, 808.3, the answer would be 4 significant figures. When you have a decimal place, in this instance 0.035, you only have 2 significant figures. And I put a box there already, the 2 significant figures, the 3 and the 5. The zeros in front are not significant. If I were to add a 0 after the 5, it would be 3 significant figures. And hopefully in the next slide, we address this. So if the question was how many significant figures in 0.0350, the answer would be 3 significant figures. In this case, the same idea, any zeros between 2 non-zero values. In this case, the 0 is between the 8 and the 3. That would be considered significant. So again, it's in this question, how many significant figures? It's 4, and they are 1, 8, 0, and 3. In this example, we have here the zeros after a decimal place are considered significant. So this is a little bit perhaps counterintuitive, because if I were to ask you 0.04, it would be 1 significant figure. But in this case, 3.0 would be 2 significant figures. So just a summary of the rules. Significant figures, 320 is 2 significant figures. If you add a decimal place there, it becomes 3 significant figures. And we'll go with this set of rules. I believe there's a slightly different definition in your textbook, Central Science, Chemistry of the Central Science by LeMay and Brown. But in our class, we'll use, if there's a decimal place, it's 3 significant figures. If there's no decimal place, it's 2 significant figures. In this particular example, 320 is 2 significant figures. 320 decimal is 3 significant figures. And to simplify, you can always write it in scientific notation here. 3.20 times 10 to the 2 is 3 significant figures. If I had written 3.2 times 10 to the 2, that would be 2 significant figures. I'm sure you're familiar with this rounding up and rounding down. If the value is 5 or greater, you round up. If the value is 4 or less, you round down. First question, how many significant figures in the following? It's 3 significant figures for A. For B, it's 1 significant figure. Because there's no decimal place here, if there was a decimal place, I put a decimal place here, how many significant figures? It would be 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. The next one, C, is 5 significant figures. 1, 2, 3, 4, 5. And the last one, we have 4 significant figures. I apologize if I'm repeating myself. The answers here are located in the bottom right-hand corner. But again, I urge you to try on your own first. We have rules for multiplying and dividing. Let me bring them up. If you're multiplying and dividing, the answer will follow the least amount of significant figures, the fewest significant figures in the question. So in this case, we have 3.21 centimeters times 5.017 centimeters times 10.401 centimeters. and I wrote there how many significant figures in each value, 3, 4, and 5. And based on our definition above, your answer should have 3 significant figures, because again in the question, the lowest one, the fewest one is 3 significant figures, 3.21 centimeters. So the final volume will be 168 centimeter cubed. Again, you have to write everything as a number and a unit. So if you were to punch these numbers directly into your calculator, you would obtain 167.50363. But when doing significant figures and multiplying and dividing, you have to look at the question, which one has the least. The 3.21 centimeters is the least with 3 significant figures. Your answer must be 3 significant figures as well. You have 167.5. You round it up to 168 centimeters cubed. If I were to ask you off the top of my head, let's say I were to ask you what 3 times 6 is based on significant figures. So that's right here, 3 times 6. A lot of times you would say 18. That is true, but according to the significant figures, the answer would be 20. Why is that? In the question, we have how many significant figures? We have 1 significant figure for the 3, 1 significant figure for the 6. Therefore, our final answer must have 1 significant figure. We round up to 20. 20 here has only 1 significant figure. So if you tell your friends and family that 3 times 6 is 20, they'll look at you funny. That's okay. We'll keep it in the chemistry. We'll keep that our little secret within our video, that 3 times 6 is 20 based on our significant figures rules. There's another rule for adding and subtracting, and it states here you have the fewest decimal places. Okay, so in this case we have 98.4 grams in the question, plus 8.125 grams, plus 0.88 grams, which equals to 107.405 grams. We look at the question. The first one has 1 decimal place. The second value has 3 decimal places. The third value has 2 decimal places. And according to our rule, we want the fewest decimal places, which is 1 in this case. The 98.4 has 1 decimal place. Therefore, our final answer has to have 1 decimal place, 107.4 grams. So a little bit different than the multiplication and dividing rule, which is for the multiplying and dividing, it's the one with the least amount of significant figures. And with adding and subtracting, it's the one with the least decimal places. So I'll give you guys a few minutes to try. Normally in class I would give you a few minutes. Yeah, I'm going to let you guys try on your own. I posted the answers again on the Common Blackboard site. Use your, I believe you learned before chemistry, the PEMDAS rule, parentheses, exponent, multiplication, dividing, adding, and subtracting. So that's the order of operations. We can do the first one. 3 times 9 is going to be 27. However, due to significant figures, it's going to be 30. Okay. So normally you could pause the video and try the problems as we go through it together. If you're not sure, just put a big question mark, so you have to remember to go back to it. Okay. Another point you'll be focusing on in your labs a lot is precision and accuracy. Accuracy is defined as how close your answer is to the true value. So here in this case we have our darts. If the center of the board is our true number, in the first case on the left we have good accuracy. We also have good precision. Precision is how close the darts are to each other. Okay, so the second one has poor accuracy because it's not close to the bullseye, but it has good precision because the three darts are close to each other. In the third case, we have poor accuracy and poor precision. The darts are not close to each other and they are not close to the center. Back to dimensional analysis. If you recall from the last set of slides, volume is length times width times height. We already stated that every time you have to have a number and a unit, 1 meter cubed, and we get the meter cubed because it's meter times meter times meter. This would be 1 meter cubed because in the question, one significant figure, one significant figure, one significant figure. Your answer has to have one significant figure. So here we have what is the volume of a box with dimensions 10 meters in length, 0.1 meter in height, and 100 centimeters in width. So you can pause the video now and try on your own. Recall that they're asking in centimeters cubed. So you'll have to convert each one of these values to, well, this one's already done for you. The width is already in centimeters. So if you recall, I'll give you a clue. 1 meter is equal to 100 centimeters. Okay? So you first convert the length and the heights to centimeters, and then you multiply the three numbers together, and you should get 1 times 10 to the 7. Again, this is worked out for you in the answers that I provide on the Common Blackboard site. For dimensional analysis, we have here a unit conversion. Here, 2.54 centimeters is equal to 1 inch. There was a time, I lived in France for a little bit. I went to their Subway sandwich store. I asked them for a 12-inch or a foot-long sandwich, and they looked at me kind of funny. Why? Because in France, they would refer to a foot-long or a 12-inch sandwich to a 30-centimeter sandwich. Okay, and like I said, it's important to use SI units so that everyone in the world uses the same numbers. For instance, if I report some research data in North America, I want someone in the other part of the world to repeat my data. I have to report it in proper units where we all understand. And again, in temperature, it's in Kelvin, length is in meters, amount is in moles, etc. So we're starting to put ideas together. In this question, how many centimeters are in 5 inches? So we write the word 5 inches. This is our unit conversion. This is an exact conversion. So 2.54 centimeters in every inch. The inches will cancel as I've shown here, and you're left with 5 times 2.54 equals to 12.7 centimeters. If the question was asked to the appropriate significant figures, how many centimeters are in 5 inches? The answer would be 10. Why? Because in this question, we have one significant figure here, one significant figure. We do not pay attention to the significant figures in the conversion factor because these are exact conversions. So one significant figure in the question, therefore one significant figure in the answer. How many centimeters are in 4 meters? So we have here the 4 meters times our unit conversion, 1 meter for every 100 centimeters. The meters will cancel and you're left with 400 centimeters. If I had written a unit conversion 1 meter divided by 100 centimeters, you could see that the meter would not cancel out with the centimeter. your final answer would be meter times meter divided by centimeter, which is not the desired unit they want. And the question says they want you to have the answer in centimeters. So the unit conversions, the conversion factor will tell you based on canceling out if you've done it right, if you put the right value on the numerator versus the denominator. These are some examples. Sometimes it's not a straightforward step. Sometimes, for instance, in the third example here, 10 milligrams into kilograms. So here you'd first convert to grams. 10 milligrams, here's our unit conversion to convert to grams. And then we have here, once we have our grams, we need to convert to kilograms. So the grams here will cancel. Grams will cancel. 1 kilogram is 1,000 grams, and then you're left with grams here on top, and it will be in your final answer. Okay. I'll show you how to use road maps later, but for instance, if you have meters in the middle, which is our SI unit, if I wanted to go from, for instance, kilometers to micrometers, you always go to the SI unit first. So if the question was how many micrometers in 2 kilometers, you first convert 2 kilometers to meters. So you would multiply by 1,000. And then from meters to micrometers, you have to multiply by 1 million. 1 times 10 to the 6. Okay, so try to remember this visually. Always go to one of the main units first. Instead of trying to go directly, in this case, kilometers to micrometers, that could be more challenging. You should always try to go to the SI unit, kilometer first. We talked about temperature. The SI unit for temperature is Kelvin. And we'll talk about this later in chapter 2. Here's an example. What is the equivalent to 298 degrees Celsius? Sorry, 298 Kelvin on a Celsius scale. And this is, room temperature. 25 degrees Celsius is about room temperature. We subtract 273 from 298 to give us 25 degrees Celsius. We saw this equation earlier to convert from Fahrenheit to Celsius. The question is, if you have a fever, 104 degrees Fahrenheit, what is your temperature in Celsius? We plug in the value for Fahrenheit here, 104. We do the math, we get 40 degrees Celsius. I'll let you guys try this one on your own. How many degrees Celsius in Kelvin is equivalent to 30 degrees Fahrenheit? How many significant figures do we have here? How many significant figures should our answer have? It should have 2 significant figures. And I look at our answer here, it has 2 significant figures. So we use the previous slide, plug in the value of Fahrenheit, which you'll have to be familiar with for your exam, and you convert it to Celsius. A reminder, you also have the online sapling homework, which you can also get practice with, how to convert from Fahrenheit to Celsius. Once you've established how many degrees Celsius, you can convert it to Kelvin by adding 273 to your Celsius value. So you would add 273 to the negative 1.1 to get you your Kelvin value. A dimensional analysis question where you're using multiple steps to get to your answer. The question is, how many feet are in 250 centimeters? So you would write out 250 centimeters. You would convert that to inches first. If you recall, the unit conversion would be 2.0 0.54 on the bottom or the top? It would be on the denominator. It would be on the bottom. So you have 2.54 on the bottom, 1 inch on the top. These would cancel, and you're left with inches. And you guys all familiar how many inches in a foot-long sandwich? It's 12 inches. So then you would multiply by, or I'm sorry, you would divide. You'd have 1 foot on top, 1 foot on top, and 12 inches on the bottom. You multiply this through, and hopefully you get there 8.2 feet. For the second one, you can pause and try, but as the hint says here, yes, you convert the pounds to kilograms first, and then from kilograms to grams, you'd have to multiply by 1,000 grams on top, 1 kilogram on the bottom. Again, these answers will be posted on Blackboard. So that's chapter 1. Only 9 more chapters to go. I hope you guys are all doing well. Again, try the sapling homework. Keep working on problems. Even go online and find other videos. Use other resources to help you out if this is not clear. Again, you can contact your instructor. You can contact me as well. Okay? So good luck, and I'll see you in chapter 2.